Statistics can be roughly divided into two different types. We have descriptive statistics, which literally just describes the data. So anytime we're dealing with mean, median, mode, or characterizing how data is distributed, that would be descriptive. Another type of statistics we will deal with later in your reading, later in the chapter, and that is inferential statistics, which involves using results from a sample to make generalized conclusions about a population. So in this video, let's talk a little bit about descriptive statistics, and I just want to hit some of the highlights in your reading and clarify some of the ideas that may be confusing as you were reading along. Okay, first of all, let's talk about mean, median, and mode. Right? So the mean we can think of as an arithmetic average of numbers. We say arithmetic because in geometry there's a different way to find the mean of numbers that involves multiplying and taking a square root. But for our purposes, you can think of this probably as the most common type of average that you're used to dealing with. So we would add up all of these numbers and divide by how many there are. And if you do that, you will find that the mean is 7.75. Okay, and then one thing you'll notice about the mean, there should be some numbers that are lower than the mean and some numbers that are higher, and that's a good check just in general to see if you're on the right track with calculating the mean. The median is just the middle number, or if you don't have a single middle number, if there are two in the middle, then you would find the mean of those middle numbers, okay, or the halfway point between them. So in this list of data, we have 8 different numbers. So we would look at the middle two and then find the mean or the average of those two numbers, which is just going to be 8.5. And then finally, the mode is the number or numbers that occur the most often, right? Or we could say have the highest frequency. So we have 2 modes in this case. We have 4 and 9. All right. Now, it is possible for a set of data to have no modes. So, for example, if we had, let's say we had 4, 4, 9, 9, and 10, 10. Okay. Now, that set of data is considered to have no mode since each number has the same frequency. Each number has a frequency of 2. Okay. On the other hand, if we were to add in one more number, so for example, 11, now we would call this data set trimodal. We would say that it has 3 modes because 3 of the numbers, 4, 9, and 10, occur with a higher frequency than the other number, 11. Okay, so if all numbers have the same frequency, either they all occur once, they all occur twice, or 3 times, then there's no mode. But if some have different frequencies that are higher than the others, then those are the modes. In your reading, you also saw the term outliers, and these are numbers that can affect usually the mean of the data, but usually not the median or the mode. Right? So notice if I put in a 100 at the end of this data, all right, then now my mode is still 4 and 9, right? And then the median, it is just slightly different because now I've added an extra number, so now the median is 9. So the outlier slightly affected the median, but it didn't have a huge impact on it. But the mean, on the other hand, if you calculate it now, the mean will be 18. All right? So outliers really do affect the average of the numbers, but don't have a huge impact on median or mode. Now, one of the things that you can do with mean, median, and mode is describe sort of an average value of your data set, or we're attempting to describe the data set with a single number. Right? So you have a choice here as to which of these measures you would use, and there are some requirements or situations where it would be better to use one or the other. So in your reading, one suggestion is that when there are outliers, you go with the median rather than the mean, and you can see why, because an outlier really does affect the mean, but it doesn't have a huge impact on the median or the mode. Okay. Another tip was to use the mode anytime we're dealing with qualitative data, all right, or things that are not quantitative. And then this is a chart from a web article, and I'll link to this so that you can see further explanation. But this just goes into a little bit more detail with the differences between the type of data that we have. All right, so nominal and ordinal, these are two words that describe qualitative data, all right, or things that are not quantities. Nominal would be sort of named categories that don't have any sort of an order, right? So if we were looking at freshmen, sophomores, juniors, and seniors, we could really rank those in any order as far as describing frequency. And then we could still count, frequency of freshmen, frequency of sophomores, and so forth. But they're not really numerical quantities. Ordinal would be also different categories that are not numerical. However, there would be some sort of a ranking. So for example, let's say we were looking at a survey of maybe the question is how often does someone watch TV each week? And maybe the choices are not at all, a little bit, somewhat, quite a bit, or very frequently. Right, so there's still sort of a ranking there from least to most, but we can't really assign values to those things. Right, so if somebody chooses quite a bit, how does that compare to not very much? Is it twice as much? Is it 3 times as much? It could differ based on how a person interprets the question. So we would consider that to be qualitative data, even if there is a number assigned to it. So if we're asking somebody to rank their amount of TV watching per week from 1 to 5, those numbers are still sort of subjective. They're not, a 5 isn't necessarily 4 more than a 1. These other two, interval and ratio, these are different types of quantitative data. All right, and I'll post a link to the article if you'd like to see more about how that's defined. But basically, we're dealing with data that's continuous. So for example, like temperatures, you can have a temperature of 32 degrees and a temperature of 33 degrees, but you can also have temperatures between those. It could be like 32.5 degrees or something like that. So we don't have separated categories like 1, 2, 3, 4. We have a whole range of different values. Okay, and then so in summary here, anytime you have qualitative data, like categories of things that are not numbers or subjective types of rankings, all right, if it's categories of data, then you want to look at the mode. If it's a ranking of data but it's still subjective, then you want to look at the median. And then for quantitative data, we look at whether the data is skewed or not skewed. Okay, so if it's not skewed, if it's fairly symmetric, and you looked at sort of the general shape for symmetric data, right? Anything that has a variety of different factors like people's heights or grades or all of the common types of data sets, okay, then you go with a mean. But if your data set is skewed, meaning there are outliers, and that was one of the hints in your textbook reading as well, okay, if there are outliers, then the median is usually a better predictor of the data. Now again, this is somewhat subjective, so part of what a statistician would do is decide based on the situation and the type of data, which of these is the best measure of central tendency. Okay, and sometimes we state some multiple options of these things, right, just to give some more information about the data. You can tell more by seeing a mean and a median than you can by just one or the other. I also wanted to talk about the term bimodal. It means two different things. All right, so if we have a list of data, it means one thing, versus if we're talking about a histogram and it's a distribution. All right, so in a list of data, the mode is just the number or numbers that occur the most frequently. So we would only call a data set bimodal if it has two numbers that occur the most with the highest frequency and where the frequency is the same. Okay, so if you have like 3 7s and 3 10s and everything else, all of your other data occurs just once, then you have two modes, 7 and 10. On a histogram with these distributions, we were looking sort of at quantities or categories or numbers that occur more frequently than others, but they don't necessarily have to be the exact same frequency. Okay, so here's an example. I like this picture. You can see we have 3 peaks, or we could say local maximums. If you've taken calculus, you're probably familiar with that term, local maximum. But we're looking sort of like at the hills, if we were to think of this as a landscape. And even though the hills are slightly different heights, we can still see that there are 3 things or numbers that occur more frequently than the other things. All right, so we would call this trimodal, whereas if we were to actually list that out, really only the highest thing would be the mode, not the other 2 that occur with slightly lower frequencies. All right, this is called trimodal as well. We have 3 peaks. Okay, this is bimodal. There are 2 peaks. They happen to be the same height, but even if it looked more like this, we would still call that bimodal. And the reason is that this sort of a picture, it could be interpreted as one set of data, but it could also be, oh, I can do better. I want one peak sort of lower. Okay, it could be one set of data, or it could be almost like we have a split with 2 different categories, and we could be actually seeing sort of 2 overlapped types of distributions. So the example here is that for time spent watching football, there's a big divide between casual fans and big fans. So, but among casual fans, there's still a more frequent watching time, and among big fans, there's a more frequent watching time, right? I see this one quite a bit on tests. Typically, there are students who are underprepared for exams, and then students who are overprepared or prepared. All right, so usually, like, there's a big split among students who fail because they didn't study, and then students who studied. And then, of course, you have a whole range of values. But, you know, if somebody hasn't studied, you know, that's almost a completely different category than people who did study for an exam. And you may see a more common score. So among those who don't study, maybe there are a lot more D's than F's. And among those who did study, maybe B's are the most common as opposed to, you know, A's or C's or something like that. All right, and then finally, let's talk about variation in data. We'll get into this in more detail in the next section of your reading, and there are some quantitative ways to describe variation. In this section, we are just looking at sort of an intuitive approach to this, and we're looking at how spread out the data values are. All right, so there are different ways to calculate this. One option would just look at the lowest data value and the highest and look at the spread between those. So you can almost look at the tails on these distributions, right? So if I look at the lowest and the highest in each one and just calculate the width there, okay, well this one in A, those are the closest together. B is a little bit farther apart, and then C is even farther apart than that. Another option is to look at where the bulk of the data is, right? So if I were to kind of circle the majority of the frequency, all right, I might do that here and sort of cut off the tail ends where there aren't many values. Okay, and then I would just look at the shape of that. Is it all squished together in the center, or is it wider? Right, and in A, it's more squished together. We've got a sharper peak. In the second one, we have a slightly wider peak, and in the third one, we have the widest peak of the 3. You can probably see that if the graphs are stretched, like you know, in Excel, I showed you can stretch a graph to make the perspective look different. It might be hard to describe something as high variation just based on the shape alone, all right? Because all I'd have to do for this low variation is just kind of pull my horizontal axis out and then squish my vertical axis in, and I could make it look a lot like this picture in C. So that's maybe a motivation for why we want to quantitatively describe variation in a mathematical way instead of just looking at intuitively the shape. But for now, at least this gives you a starting idea of what is meant by variation. Okay, those are some of the highlights for this section. If you have more questions, ask, and if not, then I'll see you in the next section.